Hello everyone. Welcome back to our channel where we dive deep into the mysteries of the universe. Today, we're playing a cosmic game of hide and seeks as we explore how small black holes might interact with the elusive supermassive black hole pairs. So, buckle up as we journey into the depths of space and uncover some astronomical secrets. In the vast cosmic arena, astronomers have devised an intriguing method akin to a game of hide and seek, using smaller black hole pairs to track down the elusive giants of the universe, supermassive black hole binaries. This innovative approach could unravel the mysteries of how these colossal black holes rapidly expanded in the universe's infancy. Black holes, despite their fearsome reputation as cosmic behemoths, are notoriously challenging to detect. Each black hole is cloaked by an event horizon, a boundary from which light cannot escape, rendering them invisible. Even the supermassive black holes, with masses millions to billions of times that of our Sun, residing at the centers of galaxies, can only be detected when they are either devouring massive amounts of nearby matter or tearing apart a stray star. However, electromagnetic radiation, which includes light, isn't the only way these cosmic mysteries make their presence known. Gravitational radiation, manifested as subtle ripples in spacetime known as gravitational waves, offers a new sensory avenue instead of merely looking for these supermassive black hole pairs. Astronomers can now listen for their gravitational symphony. This shift from sight to sound marks a pivotal advancement in our quest to understand the universe's most hidden secrets. Our approach is akin to tuning into a radio station, explains Jacob Stegman, a postdoctoral research fellow at the Max Planck Institute for Astrophysics. We're using the signals from pairs of small black holes, much like radio waves transmit music. Stegman elaborates. In this analogy, the supermassive black holes are the melodies hidden within the frequency modulation, FM, of the signals we detect. The concept of gravitational waves, first envisioned by Albert Einstein in his groundbreaking 1915 theory of general relativity, revolutionized our understanding of the universe. In this theory, Einstein proposed that gravity emerges when objects with mass distort the very fabric of reality, a four-dimensional continuum he called spacetime, which combines three spatial dimensions with one temporal dimension. According to general relativity, the greater the mass, the more severe the warping of spacetime. This explains why the gravitational pull of planets eclipses that of moons, why stars command greater gravitational forces than planets, and why black holes exert the most formidable gravitational influence of any celestial entity. Einstein also theorized that as objects accelerate through spacetime, they cause it to ring with ripples known as gravitational waves. For low-mass objects, these ripples are minute and nearly undetectable. However, when massive black holes orbit each other, a process that inherently involves acceleration, their substantial mass creates pronounced gravitational waves. As these black holes dance in a gravitational embrace, they continually emit low-frequency gravitational waves. This emission saps the black holes of their angular momentum, pulling them ever closer in a spiraling dance termed enspiraling. As they draw nearer, the frequency of the gravitational waves escalates, stripping away angular momentum at an increasing rate. This cosmic ballet continues until the black holes reach their dramatic finale, a collision that merges them into a single entity, unleashing a high-frequency scream of gravitational waves into the universe. Einstein once speculated that the ripples created in spacetime gravitational waves would be too faint to detect. He reasoned that, as they traveled across the cosmos, losing energy along the way, and considering that black hole mergers occur unimaginably far away, at distances of millions or even billions of light years, these ripples would be virtually undetectable. However, history has proven Einstein's prediction wrong. Since the landmark detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015, originating from a binary black hole merger 1.3 billion light-years away, astronomers have repeatedly captured similar cosmic events. These detections have predominantly involved pairs of stellar mass black holes, whose masses range from 3 to several hundred times that of the Sun. Yet, the detection of supermassive black hole mergers, the true behemoths of the cosmos, remains elusive for terrestrial gravitational wave detectors like LIGO VIRGO in Italy EI and the Kamioka Gravitational Wave Detector KAGRA in Japan. These colossal events continue to hide in the shadows, waiting to be uncovered. Just as our ears are tuned to pick up certain sound frequencies but not others, gravitational wave detectors like LIGO and VIRGO have their own specific frequency ranges they can monitor. Unfortunately, the low-frequency gravitational waves emitted by the dance of supermassive black hole pairs are too deep for these terrestrial detectors to hear. To put it in a musical context, while stellar mass black hole binaries hit the high notes, akin to a soprano's pitch, the supermassive pairings resonate with the deep, resonant tones of a baritone. The team's innovative strategy involves detecting subtle shifts in the gravitational waves from stellar mass black hole binaries, influenced by the overlapping waves from supermassive binaries. These minor fluctuations could unveil the presence of supermassive black hole mergers, which currently blend into a background hum only detectable by massive networks of rapidly spinning neutron stars known as pulsar timing arrays. The crux of this idea, explains Jacob Stegman, is to harness the high frequencies we can easily detect to explore the lower frequencies that are currently beyond our reach. This proposal not only sheds light on the mysteries of supermassive black hole mergers, but could also guide the development of future gravitational wave detectors, such as the upcoming LISA Laser Interferometer Space Antenna. This space-based detector is a collaborative venture between NASA and the European Space Agency ESA. With LISA's path firmly established following its adoption by ESA last January, it's crucial for the scientific community to determine the optimal strategy for the next generation of gravitational wave detectors, explains Lucio Mayer, a black hole theorist at the University of Zurich. This includes deciding which frequency range to focus on. Our study strongly supports prioritizing a detector design that can tap into the DC Hertz or low frequency range. First things first, let's define our players in this cosmic game. Black holes are regions in space where the gravitational pull is so strong that nothing, not even light, can escape from them. They come in various sizes, with the small ones being up to 10 times the mass of our Sun and the supermassive giants weighing millions to billions of solar masses. These supermassive black holes usually reside at the center of galaxies, orchestrating many of the cosmic events around them. Now, on to the main event. How do small black holes play hide and seeks with supermassive black hole pairs? This game begins when small black holes wander close to these massive structures. Due to their immense gravitational forces, supermassive black hole pairs can capture small black holes. This interaction is not just a simple capture, it's a complex dance where the small black hole can either settle into an orbit around the pair or get ejected at high speeds into space. Studying these interactions is crucial for astrophysicists. It helps them understand gravitational waves, ripples in space-time created by moving objects like black holes. Observing small black holes around supermassive black hole pairs could provide new insights into how gravity works under these extreme conditions and even offer clues about the dynamic processes that govern galaxy centers. Detecting these interactions poses significant challenges. The main issue is the sheer scale and distance involved. These cosmic events are happening millions to billions of light years away from us. Moreover, small black holes are difficult to observe directly because they do not emit light. Scientists rely on indirect methods like monitoring the gravitational effects on nearby stars or gas clouds to spot them. With advancements in technology and methods like radio astronomy and space-based observatories, we're getting better at spotting these elusive cosmic players. Future missions are expected to provide more data that could illuminate the mysterious dynamics of black hole interactions. This research not only enriches our understanding of the cosmos, but also tests the limits of our physical theories. Gravitational waves are ripples in the fabric of space-time that travel at the speed of light. These waves were first predicted by Einstein's theory of general relativity and were confirmed a century later by observatories like LIGO. When small black holes interact with supermassive black hole pairs, they can generate these waves, providing a unique way to study the interaction from Earth. Detecting these waves allows us to understand the mass, distance, and even the spin of the black holes involved. Imagine a cosmic ballet, where the small black hole is a dancer trying to find its place amidst two enormous partners. The gravitational forces at play cause the small black hole to either spiral inward, leading to a possible collision, or be flung outward into space. This delicate dance can last millions of years, and the gravitational energy exchanged in this process is what creates the gravitational waves we can detect. Supermassive black hole pairs often form when two galaxies collide and merge. These mergers are not just spectacular collisions of stars and gas, but also involve the merging of their central black holes. Understanding how these pairs interact with small black holes can give us insights into galaxy formation and evolution, a process that has shaped the universe we see today. The orbits of black holes around each other and around supermassive pairs are governed by complex dynamics. These orbits can be highly elliptical, meaning that the small black hole may come very close to the supermassive pair at times and then swing far out. Studying these orbits helps scientists predict the future behavior of these systems, such as whether they will eventually merge or remain in stable orbits for billions of years. Interestingly, our own galaxy, the Milky Way, is believed to harbor many small black holes that are hidden from view. These could potentially be interacting with the supermassive black hole at our galaxy's center, known as Sagittarius A. Understanding these interactions in other galaxies can help us make predictions about what's happening closer to home. Simulating the interactions between small black holes and supermassive black hole pairs is no easy task. It requires complex models and powerful supercomputers to account for the vast range of forces and conditions at play. These simulations are essential for testing our theories about gravity and the behavior of matter under extreme conditions. One fascinating outcome of the interaction between small and supermassive black holes is the possibility of mergers. If the conditions are just right, a small black hole could spiral inward and eventually merge with a supermassive black hole, releasing a tremendous amount of energy in the process. This event would produce an intense burst of gravitational waves, detectable across vast distances. After a black hole interaction or merger, the resulting system is often left in a different state than before. Scientists study the aftermath by observing changes in the environment around the black holes, such as the movement of nearby stars or gas clouds. These observations help confirm whether a merger or interaction has occurred and provide data on the final configuration of the black holes. Dark matter, the mysterious substance that makes up most of the universe's mass, could play a role in the dynamics of black hole interactions. Though we cannot see dark matter directly, its presence could influence the gravitational forces at work, affecting the orbits of small black holes around supermassive pairs. Understanding this influence is key to unraveling the nature of dark matter. A particularly interesting phenomenon is the slingshot effect, where a small black hole gains immense speed after a close encounter with a supermassive black hole pair. This happens when the small black hole gets caught in the gravitational pull of the pair and then gets flung out at high velocity. These slingshot events can propel black holes across the galaxy and even into intergalactic space. Interactions between small black holes and supermassive pairs could also be a source of high-energy cosmic rays. These particles travel at nearly the speed of light and are detected on Earth as part of the background radiation. By studying the origins of cosmic rays, scientists hope to link them to specific black hole interactions and learn more about these powerful cosmic events. Black hole interactions can have a significant impact on the surrounding environment, including star formation. The intense gravitational forces can compress gas clouds, leading to the birth of new stars or disrupt existing star systems, flinging stars out of their orbits. Understanding this process is crucial for explaining the formation of stars in the dense regions near supermassive black holes. Time behaves differently near black holes due to their immense gravitational pull, a phenomenon known as time dilation. For a small black hole interacting with a supermassive pair, time could slow down significantly. This means that while millions of years pass for an observer far away, the interaction might seem to unfold much more slowly for an observer close to the black hole. Supermassive black holes are often surrounded by accretion disks, which are rings of gas and dust that spiral into the black hole. These disks play a critical role in feeding the black hole and can be influenced by the presence of a small black hole. The interaction between the small black hole and the accretion disk can lead to the release of intense radiation, observable as bright flares from Earth. In the search for small black holes interacting with supermassive pairs, scientists also look for binary black holes, two small black holes orbiting each other. These systems can eventually spiral inward and merge, creating another source of gravitational waves. Detecting these binaries, especially when they interact with supermassive black holes, provides a rich field of study in gravitational wave astronomy. The spin of a black hole, which is how fast it rotates on its axis, can greatly affect its interaction with other black holes. A small black hole with a high spin might behave differently when captured by a supermassive black hole pair compared to one with a slower spin. Understanding these differences helps refine our models of black hole physics and the dynamics of these complex systems. Black holes can serve as cosmic time capsules, preserving information about the early universe. When small black holes interact with supermassive black hole pairs, they can reveal clues about the conditions present when the universe was young. By studying these interactions, scientists hope to learn more about the early formation of black holes and the galaxies they inhabit. Magnetic fields can also play a role in black hole interactions. While black holes themselves do not have a magnetic field, the matter around them can generate powerful magnetic forces. These fields can influence the motion of small black holes as they approach supermassive pairs, affecting the dynamics of their interaction and the energy released during these events. One of the most spectacular phenomena associated with black holes is the formation of cosmic jets, narrow beams of particles that are ejected at nearly the speed of light. These jets can be generated during the interaction of a small black hole with a supermassive pair, especially if the interaction disturbs the accretion disk around the supermassive black hole. These jets are powerful enough to extend for thousands of light years, shaping the structure of the host galaxy. As our technology and methods continue to improve, the study of black holes will only become more refined. The next generation of observatories and telescopes, both on Earth and in space, will allow us to detect black hole interactions with greater precision and over greater distances. This will lead to new discoveries and possibly even more questions about the nature of these enigmatic objects. Black hole interactions also offer a unique laboratory for testing theories of quantum gravity, which seeks to unify general relativity and quantum mechanics. Observing the behavior of small black holes near supermassive pairs could provide crucial data that helps physicists develop a complete theory of gravity that works on both cosmic and subatomic scales. Some theories suggest that black holes could be gateways to other universes, or even serve as seeds for new universes in a multiverse. While highly speculative, the interactions between small and supermassive black holes might offer clues to these exotic ideas, pushing the boundaries of our understanding of the cosmos. Humanity has long been fascinated with black holes, from their mysterious nature to their depiction in science fiction. Our study of these objects reflects our desire to understand the universe's most extreme environments. Each new discovery about black hole interactions fuels our imagination and expands our knowledge of the universe. As we advance our capabilities in space exploration, understanding black holes becomes increasingly important. Whether it's for navigating around these massive objects or harnessing their energy, the knowledge we gain from studying black hole interactions will be crucial for future space missions. When black holes merge, they release an enormous amount of energy, enough to affect their entire host galaxy. These events can trigger star formation, alter the orbits of nearby stars, and even influence the overall shape of the galaxy. By studying these cosmic impacts, we gain insights into how black hole mergers contribute to the evolution of galaxies. The study of black holes and their interactions is a global effort involving scientists from around the world. International collaboration is crucial for advancing our understanding, as it allows for the sharing of data, resources, and expertise. This collaborative approach has already led to groundbreaking discoveries, such as the first detection of gravitational waves. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.